Now, if you just look at page 8 of your notes, okay, this one is describing to you how would you determine the specific latent heat of vaporization, how would you determine the amount of heat that is required to cause a phase change from liquid to gas. Okay, so how you will do this is by doing something like this. You will first contain the liquid that you're trying to test inside some sort of gas flask. That gas flask actually has some holes in it. So what you will then do is that you want to heat up this liquid using an electrical immersion heater that is again connected to a voltmeter and an ammeter so that you can actually calculate out the amount of heat energy that you supply to it. Okay, so you heat up that liquid, the liquid will boil, it becomes gas. So that gas will actually seep out through holes inside your gas flask and it will try to flow and escape to whatever outlet or opening that is available. So this gas flask with holes that you contain the liquid is actually contained inside another bigger apparatus. Okay, you can think of this as another bigger gas flask where it is connected to some sort of condenser. So what will happen now is that once your liquid vaporizes, it will try to escape. This is the only outlet that you have. That liquid, that vapor will try to escape through here. But at the same time, because you have a condenser with cold water running in and out here, that gas that is flowing out will suddenly condense back into liquid. And below it, you will put some sort of beaker to collect the condensed liquid. Okay, so right now, if you have wanted to find out the specific latent heat, the general principle is that because Q is equals to ml, L is equals to Q over M. This part here, when you're trying to find out the Q, this one we know is the heat supplied. We can actually find it by using VIT. That's the reason why we use an electrical immersion heater in the first place. Okay, so the issue now is finding out this mass M. Now, this mass M here is not the mass of the liquid originally. Instead, it is the mass of liquid that has changed to gas. Okay, it's more accurate to consider this mass as the mass that has changed phase. Okay, that's what we want to find here. So you are trying to find out the mass of liquid that has changed to gas, the mass that has actually changed phase. That's the reason why we put the beaker here to collect back that condensed liquid. Okay, but you cannot use this mass directly in the first place. Okay, what we will say is that you actually have to wait a while before you can actually use the value of mass. Okay, so in the first place, when you started this experiment, your liquid will boil. It changes from liquid to gas. It starts condensing. So you continue your boiling until the temperature of all parts of the apparatus have steadied. Okay, and during that time, you keep collecting the condensed vapor or condensed liquid over a specific time interval of T, say maybe every 5 minutes. So you repeat this every 5 minutes until you notice that the mass of the liquid collected per unit time interval is constant. Okay, is at this point here where you get a constant mass of liquid per unit time interval that we say that you have actually reached what we call constant boiling rate. Okay, so if you try to tabulate out the mass of water condensed collected every 5 minutes, say this is the first trial, second trial, third trial, fourth trial, and fifth trial. Notice how the mass of the liquid collected changes. At first it was 23, then it was 32, and then subsequently it became 45, and it remained at 45 and 45. This part here is where we say that you have actually reached constant boiling rate. Okay, so you actually have constant mass of liquid per unit time interval here. Okay, so once you have reached this part here where you have constant boiling rate, where you have constant mass of liquid per unit time, that is the mass that you will use for this equation. Okay. Now, sometimes they don't give you a table. Sometimes they give you a graph instead. From the graph itself, you should be able to recognize when you reach constant boiling rate. Let's just say, for example, they give you a graph of total mass of liquid inside the beaker with respect to time. Say this time you just keep on collecting the condensed liquid inside your beaker. You don't throw it away. You just keep on collecting it from t equals to 0 seconds all the way to t equals to 30 minutes without even throwing it away. You just keep collecting and measuring the mass. You ought to get a graph that looks like this. Okay, so you can imagine that as more and more liquid condenses and drops into the beaker, the mass will increase, right? So you will notice that initially it is a curve, but after that it starts to become a straight line. Okay, once it becomes a straight line like this is where again you reach constant boiling rate, because here is where you again have constant mass of liquid per unit time interval. You have constant mass of liquid that has changed to gas per unit time interval, because if you divide this portion here into 3 equal parts, this one here is delta t, this one here is delta t, and then this one here is delta t. Look at the change in your mass. If you use a ruler to draw it carefully, this is your change in mass, this one is the change in your mass, this one is the change in your mass. They're all actually going to be the same. It is akin to you having this constant mass of liquid converted to gas per unit mass. Okay, so that is one thing to take note of here. Now, if you then want to apply conservation of energy for this particular case when you're heating the liquid to gas, what you could say is that the electrical energy, let me clear off whatever you have here. What you could say is that the electrical energy that you supply is equals to the heat gain by the liquid to vaporize, as well as the heat loss to the surroundings. Okay. Now, different from the first two examples, you cannot just simply say heat loss here is negligible. Because if you look at your apparatus right now, this apparatus is actually quite big with a lot of holes in it. You have a condenser in and out. You have an outlet here for your gas to escape. So cannot possibly insulate this entire apparatus to minimize heat loss. It is very, very difficult. So here, when it comes to determining the specific latent heat of vaporization, it is very difficult to insulate it. So your heat loss here will be quite significant. Okay, you cannot just simply ignore it. But there is a way to go around it in order for you to find out your latent heat of vaporization. That one is by doing the experiment twice. Okay. Now, when you first did your experiment, convert your liquid to gas, you will use a certain power setting. You use a certain PD and current for your electrical immersion heater. Okay, for that power setting that you had, you will collect out the mass of liquid as converted to gas when it has reached constant boiling rate. This is the equation that you will get. Okay. V1 I1T equals to M1 LV plus H, where LV is your latent heat of vaporization. What you then do is that you subsequently repeat the experiment again, but using a different power setting, meaning to say you use a new heater current and new PD, and you collect a new mass of liquid that has converted to gas. Okay, the value would be different because you're using a different power setting now. Okay, so you collect the new mass of liquid that has converted to gas or vapor, but make sure that you collect it over the same time interval t. If you look at the previous portion here where you first conducted the experiment, you collected the liquid, condensed liquid every 5 minutes. When you repeat the experiment again, using a different power setting, different current, different power, make sure you're using the same time interval too. If you did it over 5 minutes, you must also use 5 minutes too. Okay, there's a reason for it, which will be explained later. So if you conduct it with a different power setting now, you again apply conservation of energy, your energy equation should become V2 I2T equals to M2 LV plus H. Okay, Now you have two equations here. What you just need to do is that you take equation 2 minus equation 1. All right, assuming that this heat loss H and this heat loss H are the same, if you take equation 2 minus equation 1, they will actually minus off each other, leaving you with this final expression where B2I2 minus B1I1T equals to M2 minus M1 LV, from which you can find out your specific latent heat of vaporization. Okay. Now, in your case, just now I mentioned to you that you can assume that these two heat losses are the same. It's only by assuming that both these heat losses are the same that your heat loss can be eliminated from the equation. Now, we can say that it's the same because of two things. This one, you have to look at page 9, the next page. We can say that the heat loss is the same because, number one, you had same time of exposure. All right. The time taken T is the same for both cases. You're using the same time interval here of 5 minutes. That's the reason just now I emphasized to you, you must always use back the same time interval. So you had same time interval in the first place for both cases. And also you had same temperature difference when you were conducting the experiment. Because you see, let's assume that this one is water. You're trying to find the specific latent heat or vaporization of water. When your water boils, it will be at 100 degrees centigrade. This one will be at a constant temperature because it's at boiling point. And then assuming that you're conducting it in some reasonably cool room, maybe this one is 25 degrees centigrade. When you did this experiment, you did it twice using two different power settings. So under both circumstances, under both settings, you're still heating water to 100 degrees centigrade and you're still conducting it inside the same room. So the temperature difference here is just going to be 75 degrees centigrade for your first power setting and for your second power setting. Your temperature difference here is the same. So these two factors here actually contribute to your heat loss being the same for both cases. Okay, so let me just explain a bit further about these two factors. If I talk about exposure time, how does it actually affect my heat loss? You consider that you have two beakers here now. This is beaker A, this is beaker B. They both contain water, all right? Say this one is at 100 degrees Celsius. This is also 100 degrees Celsius. But this one, beaker A, I just leave it for 5 minutes outside. Okay, say this one, I just leave it for 5 minutes outside. And then for beaker B, I leave it for 60 minutes outside. Okay, I leave it for 60 minutes outside. And when I say I leave it outside, I mean that I leave it at room temperature. Okay, so here for beaker A, the room temperature could be 25 degrees Celsius. And then for beaker B, it also could be 25 degrees Celsius. Okay, everything else remains the same. The only thing different is the exposure time. Okay, so when you're talking about the heat loss, then you can imagine that the heat loss from B would definitely be more than the heat loss from A, isn't it? Because here, you have longer exposure time. When you have a longer exposure time, you have more time for heat to be lost. Okay, more time for heat to be lost to surroundings. For beaker A, your heat loss was only for 5 minutes. But for beaker B, your heat loss was for 60 minutes. So obviously, what you could say here is that if your exposure time increases, your heat loss ought to increase. Okay, so this is the effect of exposure time. But how about the effect of temperature difference then? So again, let me just try and draw for you two different examples. So if you're talking about temperature difference, again, you have two beakers to consider. Say this one is beaker C, and then this one is beaker D. They are both containing water. Again, say this one, they're both at 100 degrees Celsius. They're boiling water. Okay. And these two, I leave it outside for the same time. Maybe this one is for 10 minutes. And then this one is for 10 minutes also. Okay, but I leave it at two different rooms. Maybe this one, beaker C, I leave it at room temperature, where it is at 25 degrees Celsius. Okay, whereas for beaker D, I leave it in the freezer. I purposely put it inside the freezer where the temperature is negative 10 degrees Celsius. Okay, so now, with this in mind, which one will tend to have a larger heat loss? You can probably say that in your case here, heat loss from D would be more than heat loss from C. Because here, if you look at the temperature difference, this one, the temperature difference is 75 degrees Celsius. Okay, maybe I make the case even more exaggerated. Maybe this one, I put it in a very hot room. The room is at 40 degrees Celsius. So my temperature difference here is just going to be 60 degrees Celsius. And then for the one that I put inside the freezer, this temperature difference is going to be 110 degrees Celsius, almost double that of C. Okay, so here you can say that the heat loss from D will be more than the heat loss from C. Okay, because the temperature difference is larger. So if I wanted to write something about it, this is probably what I will say. The larger the temperature difference, the greater the heat loss. Okay, so meaning to say if delta T, the temperature difference is large, your heat loss will be large too. Okay, so these two are actually the things that could affect your heat loss. So if you refer back to the experiment that you just done, under the two different power settings, you use the same exposure time of 5 minutes, you use the same temperature difference of maybe 100 degrees Celsius with room temperature 25 degrees Celsius. Because these two are the same, your heat loss can be assumed to be the same. So once you ensure that these two factors are the same, your heat loss can cancel off. You can now determine your specific latent heat of vaporization accurately. Okay. Now, you doing it this way actually will allow you to determine an accurate value of your latent heat of vaporization. This one is not going to be an overestimation or an underestimation. Okay, right? Now, if there's anything that you need to know about using different power settings, if you use a different power setting, it will only affect the time taken to reach constant boiling rate as well as the amount of liquid collected per unit time. In other words, if say you use a higher power setting, maybe from 50 watts, you suddenly change to 200 watts, you will actually reach constant boiling rate faster and you will tend to have more liquid collected per unit time. Okay, that's the only effect that using a higher power will do for you. Okay, but for all manners and purposes, the latent heat of vaporization for the liquid that you're testing will still be the same. Okay, so that is for the concept part here. And concept part is okay already for thermal properties. So let's just do one or two questions